Let's continue on to part C here. This is our piecewise defined function. We have anywhere that it's less than or equal to 0, you're using the function x plus 1. Anywhere it's greater than 0, you're using the function e to the x. I noticed that x plus 1 is a polynomial function, so it would be continuous negative infinity to infinity. I noticed that e to the x is an exponential function, which is also, its domain is negative infinity to infinity. It is also continuous, negative infinity to infinity. So we only have one trouble spot, and that's at the spot when x equals 0. So the question is we're looking at a picture here where we have a function to the left of 0 and a function to the right of 0. Do those functions agree? Essentially, does that limit exist? And if you remember from the previous section 2.2, how do we handle piecewise defined functions? All we have to do is plug in that x value into each of those functions. So look at 0 plus 1 when we put it into the first function is equal to 1, right? And then we're going to look at e to the 0, which is also equal to 1. So I'm plugging 0 into both of one of those. Since they're the same, we know the limit exists, we know the point exists, so the limit exists, the point exists, they're the same thing. That means it's continuous at that point. So again, x plus 1 continuous everywhere, e to the x continuous everywhere. The only place we had question was at x equals 0, which it's continuous there. So that means it's this function h of x is continuous everywhere, or the interval negative infinity to infinity. Last one, d, y equals sine of x. That's our transcendental functions. If you think about the graph of sine of x, looks something like an S, but you do have to remember that it continues on forever in both directions. You're thinking about what's the domain of sine of x. It's defined everywhere. We can plug in any x value we want. So the answer would be negative infinity to infinity. Let's continue on with one-sided limits and continuity on closed intervals. So it says to understand continuity on closed intervals. Notice every single time we've used open intervals, parentheses, right? So what does it mean to put a closed interval on it, and can we put a closed interval on it? It says to understand continuity on closed intervals, you first need to look at different type of limit called a one-sided limit. For instance, the limit from the right or right hand means that x approaches c from values greater than c. This is denoted by the limit as x approaches c. If you see, the only thing new here is this little positive sign. Anytime you see this little positive sign right here, that just means from the right. Okay? And then the next one says, similarly, limit from the left or the left-handed limit. So what do we have for notation for that? You have a little c to the negative sign. This just means from the left. So we've already done this. We've already done limits from the left and the right because we realized that limits from the left and limit from the right need to be equal. We just never formalized it. But I want you to think back to some of the examples that we did when we had an x values and we had our function values or y values. When we did this, we would be looking at something like, I don't know, x equals 0, right? Sorry, x equals 0. And we would do some numbers from the left and we would do some numbers from the right. So we did things like negative 0.1, negative 0.01, negative 0.001. Likewise from the right, we did 0.1, 0.01, 0.001. Okay. Well, this one would be from the right. The 0.1, 0.01, 0.001, that's as we came from the right. And the other one would be as we came from the left. So we've already done it, we just never formalized it. We wrote it in English. We literally said, as we come from the left, it approaches this value, or as we come from the right, we approaches this value. Now we just have some nice notation to help us out. When we do it, it's the limit as x approaches c with a plus means from the right, and limit as x approaches c with a minus means from the left, okay? So it says, examples, one-sided limit. It says, find the limit of f of x equals the square root of square root of 4 minus x squared as x approaches negative 2 from the right. So what does that mean? That means really what we're finding is this right here. We need to find the limit as x approaches 2 with a positive sign. Again, this means from the right of square root of 4 minus x squared. So why is that important? Why do we care about that? So what I just caught is a typo on this. That's why I kind of hung up for a second. this right here, it says 2 from the right, and I was thinking about plugging in numbers bigger than 2 into here, and so that number would be bigger than 4, so you would have 4 minus 4, which would be a negative number, or 4 minus a number bigger than 4 would have been a negative number, so square root of a negative number doesn't exist. So I knew this didn't exist. I knew something couldn't be right. So this was a typo on this one. This was supposed to be the limit as x approaches negative 2 from the right of this function. Okay, so what that means is we need to plug in numbers that are just to the right of negative 2. Well, what's the nice thing is we know this is a continuous function, and for a continuous function, a radical, we can always start by trying to plug in the number. So this would be 4 minus negative 2 quantity squared, which would be 4 minus 4. So we have the square root of 0, which is just 0. So our answer here would be 0 because we could just plug it in. Kind of. I mean, that's kind of, because what I want you to do is I want you to consider the graph of this. The graph of the square root of 4 minus x squared, well, that's half of a circle centered at 0, 0 with a radius of 2 is really what that is. And so here's the x value of negative 2. Notice if we come from the right, it's absolutely correct that our y value does approach the y value of 0. But if I said, does the limit exist at negative 2, there is nothing to the left of it. To the left of it, this function's undefined. So you can't talk about the limit as x approaches negative 2 of this function because the limit doesn't exist. There's nothing to the left. But we certainly can talk about the one-sided limit. Can't talk about it from the left. Can't talk about it at the point because it doesn't exist. But we can talk about it just from the right because we are able to plug in values just to the right. So yes, we can just plug in the number 0, get the answer, but I really want you conceptually to think about this. If I said, what is the limit as x approaches negative 2, and I didn't say left or right, even though you could plug in the number 0 and get the number 0, it still wouldn't work. Because that's one of the places where the domain is restricted, and we have to be very, very careful on this one. So, one-sided limits, yeah, just plug them in. You can think about it that way, but be very careful because it might exist from one direction but not the other. Why do we really care about this? Well, let's go back to this graph right here. If I said, where is this graph continuous? Well, certainly its domain is negative 2 to 2, so you could certainly say that it's continuous on the interval negative 2 to 2 with parentheses without a doubt. But the question then becomes, could you use brackets? And this is where the limit, or it depends on the textbook, and it depends on the one-sided limit. Can we include the number negative 2? And the answer is yes, we could actually include the number negative 2 because the limit from the right exists and it's equal to the function value. Likewise, could we include the number 2? The answer is yes, we could include the number 2. Why? Because the limit from the left exists and it's the same as the function value. So in this case, we could actually use brackets for the interval of continuity, but we have to be careful defining the interval of continuity here using brackets because technically the limit doesn't exist at that point. Only the one-sided limit exists at that point. So I'm not trying to convince you, I'm trying to say this is very serious. We have to think about what's really going on at this point. Is the function defined at that point? Does the limit exist at that point? Well, here we only need to consider one-sided limits to be able to do brackets. Another function that you're going to see several times throughout the semester is called the greatest integer function. Okay, so what is the greatest integer function? It's the greatest integer in such that it's less than or equal to x. In other words, round down. That's what the greatest integer function means to me. It just means round down. Even if you had 2.9, you would round down to the value 2. Even if you had 2.9999999, you would still round down to the number 2. Notice the greatest integer function, if you plug in the number negative 2, if you round down, I don't want you to think that it's rounding down to the number negative 2. Rounding down in this sense means the number that's smaller than it, so it's actually negative 3. So anytime your input is a positive number, you always round down. Anytime it's a negative number, rounding down technically means round up but make the number negative. That's really down, right? Because -2 is actually above -3, or more so I should say -3 is below -2.5. So rounding down really means go down to that integer below it. So that's called the greatest integer function. Anytime it's a positive number, it's just going to round down. Anytime it's a negative number, it rounds that number up but makes that number negative still. So it's not quite like the absolute value function. Be careful with that.